Good afternoon. My name is Jennifer Curtis. I'm the Dean of the College of Engineering here at UC Davis, and turnout's terrific. We may be, while our speaker is giving the presentation, getting more chairs out so that no one has to stand. So we will be bringing in some more chairs. So I want to welcome you all to our winter College of Engineering Distinguished Lecture. And as you may know, these lectures, these college-wide lectures, bring the most prominent academic and industrial experts to UC Davis. And the idea is for them to interact and exchange ideas with our faculty and students. But before I welcome our distinguished speaker, as you all know, the importance of safety in our college, and we're starting to have safety moments before some of our events. And our quick safety moment is, since the talk is on storage of energy, a quick safety moment about minimizing risks associated with lithium batteries, which are common in many of the gadgets today. So these batteries work well, but they can create fires by overheating, charging, or having damage to them. So I urge you that to store these batteries at room temperature, and also when you're storing or recycling the batteries, that the ends do not touch. So you can place tape on the ends to prevent fires associated with these batteries. So thank you for helping us foster a culture of safety in our college. So without further ado, it's my great pleasure to welcome today's speaker, Dr. Lynden Archer. Dr. Archer is the James A. Friend Family Distinguished Professor of Chemical and Biomolecular Engineering at Cornell University and the David Croll Director of the Cornell Energy Systems Institute. Dr. Archer received his PhD in chemical engineering from Stanford University, and he was a postdoctoral scholar at AT&T Bell Labs. He is also a member of the National Academy of Engineering, and he is a fellow of the American Physical Society. Today, Dr. Archer will be discussing how rechargeable electrochemical cells offer the potential for transformative advances in cost-effective storage of electrical engineering. Now, please join me in giving Dr. Archer a warm UC Davis welcome.
Thank you. So first, Jennifer, thank you for that warm introduction. And thank you all for coming. This is quite an audience here. And so I look forward to sharing with you what we've been working on, actually now for about a decade, on this question of energy storage. Now, my College of Engineering has adopted this motto of breaking the rules. And so almost every Cornell talk you'll see these words, breaking the rules. It basically means that rules are rules, they're not laws. A rule becomes a law when it's tested in every possible context and then it's found to be true. And so here, the essence of what I'm going to tell you is that there are certain truisms about conditions under which batteries that use metal anodes can operate that we've discovered by just applying the principles of chemical engineering, transport phenomena, stability, analysis, that these rules are not laws. And in so doing, we've actually uncovered example after example of energy-dense chemistries, aluminum, lithium, zinc, that have exceptional promise for lowering the cost of energy storage. So that's the gist of what I'm going to tell you today. Now, to get us started, I want to start kind of somewhat at a start for me. And this is the National Academy of Engineering's list of 21st century grand challenge problems that they basically published and conceived around 2008 or so. And if you look at this list, I mean, you see that the first two are by no accident energy related. And if you think a little bit about this list, it's, first of all, the first one isn't novel at all, in part because every bit of energy that we consume and use in our world actually originated from the sun. And it's the energy that's trapped in the bonds, the carbon-carbon bonds in fossil fuels, is the energy that we use to power our lives. And so the essence of this target was to make that energy more affordable and more accessible. Now, what is interesting is that a second grand challenge, which is energy from fusion, anticipates the obvious in that the sun actually generates energy from a fusion reaction. So you can interpret these two challenges as saying, well, you either learn how to use the energy from the sun or build your own sun. All right? And so the question then is, short of building our own sun, which people think is somewhat, of a 50 to 75 year challenge, could we do better in terms of energy harvesting from our existing sun? Now, in 2008, when this set of challenges was articulated, the perspective was that these were challenges. And one of the real shockers has just been how the price of solar energy has just plummeted over the last decade or so, such that now in regions pretty much all over the US, the levelized cost for solar energy is approaching 5 to 6 cents a kilowatt hour, and people like Nate Lewis have argued it could go as low as 2 cents a kilowatt hour. And what is interesting about that is that that is competitive with energy generated from fossil fuels. And so perhaps obvious question is that if the costs are so low and the technology, silicon technology, is so accessible, it's what we use in our personal devices, why isn't energy from the sun being better utilized in making our society a lower carbon footprint society? And the answer basically has to do with two things, right? The first is here, that the energy from the sun is intermittent, and a simple way of saying it is that the sun doesn't always shine. And so obviously you need some mechanism of storing the extra energy when it's available in abundance so that you can use it when it's not. But the corollary to that is that the current storage technology is actually pretty expensive. It's not expensive for transportation, where cost can be somehow factored in terms of battery cost in a relatively small fraction of overall cost to make the entire EV, in my example, affordable. But the power generation community is extremely stingy in terms of increasing costs, because obviously the customer pretty much at every status level, every income level in society has to carry that cost equally. So it's something one has to be very thoughtful about when you change the cost structure. So the elephant in the room is really about humanity's carbon footprint, right? So we are only talking about this problem because there's another problem. And the other problem is that most of the technologies we use today for generating energy also generate carbon dioxide emissions. And so this chart tells you that the power generation, which is the area we've made such dramatic progress, only constitutes about 28% of the US greenhouse gas emissions per year. The other big contributor is transportation, and the next one is actually manufacturing. And it's just shocking that these three combined makes up about 80% of the greenhouse gas emissions in the US. So the thought is that if we can design energy storage technologies that are capable of working for all three, this would be a pretty major breakthrough for society. So I think this is hopefully self-evident. So this is the summary of what I just said. So we want to design better batteries so that we can balance intermittency in solar and, turns out, also wind generation technologies. Then of course there's you, right? So you don't want this phone, right? You want this, or perhaps better yet, one that you can't see, that's somehow implanted, that just rings, right? And if you talk to the people in the know, they will tell you to get that kind of power in something that's invisible or small, it means that the energy storage has to be just phenomenal, well beyond what we can achieve today. And then of course there are these cool things, right? This stuff is now old news, right? This stuff is always beautiful to look at. And this stuff is actually on the horizon. It's just amazing the advances that have been made in autonomous robotics in the last 10 or so years. And if you listen carefully, as I do, you'll notice that they're always very noisy. And the reason they're noisy often is that they're either carrying around your lawnmower engine to be autonomous, or they're carrying around a cable that's plugged into a wall, in which case they're not. And so again, if we're going to basically reap the benefits of these sort of aids in manufacturing, in industry, we're going to need to find as reliable methods for storing energy and delivering it as we've figured out for powering humanity. So let me talk just briefly about the technology du jour, right? So this is a big deal. So lithium-ion batteries won the Nobel Prize in Chemistry this year. So Stan Whittingham contributed by first understanding intercalation chemistry in titanium sulfide. John Goodenough figured out how to do that at higher potential. And a large group of Japanese persons, including Yoshiono, discovered how to remove lithium metal from the original battery designs and to replace it with carbon. So the lithium-ion battery we know today has a lithium carbon 6 composite as the anode, and just notice there's 6 moles of inert carbon for every mole of lithium, and that turns out to be important. It has a cathode that's some layered material. The grandfather of these cathodes used to be the lithium sulfide. It has a separator, which is a plastic device that essentially just is there to keep the two electrodes from touching. So its principal property is that it has to be permeable to the electrolyte that saturates the two electrodes, but it also has to be electronically insulating. So in case things touch, there are no internal shorts. And then of course there's an electrolyte, a fluid that carries pretty much all of the charge. So this is great, but the challenge, as I said before, has been cost. So my colleague Yetming Chang came up with this beautiful chart that was actually published in 2017 in the journal Energy and Environmental Sciences, and we've actually added to this chart. And what he decided to do is to look at the cost of different energy storage technologies over time. And the idea is that the energy generation industry tells us that we need to basically be able to get acquisition costs below $100 a kilowatt hour. Now notice the y-axis is a materials cost. And the reason for that is about 60% of the cost of a battery is the materials cost. So this cost doesn't decide everything, but it certainly decides a pretty substantial fraction of the overall cost. And so it is thought to be a good kind of barometer of the cost characteristics. Now, so this $100 a kilowatt hour, you have to understand that it's a cost that actually, if you compare it to the 5 or 2 cents a kilowatt hour for generation, this is a non-starter. But the idea is that because a battery is a closed system, if that system can operate for 1,000 cycles trouble-free, then the amortized cost becomes 100 over 1,000, right? And so it becomes then something that's competitive. Now, if you look at this chart, you will see that lithium-ion chemistries in a variety of configurations are very close to this line. And this is, in fact, what has generated the excitement in the community, that lithium-ion batteries, the ones today, can meet these cost characteristics. But what caught my attention is that as you go downwards on this chart, to systems that cost 10 cents a kilowatt hour, $1 per kilowatt hour, this is acquisition cost, not even figuring out the cycle life, at the lower amortized cost, you notice that there are lots of chemistries. And if you look more carefully, you'll notice that in every case, these batteries use metals as the anode, not the composite carbon. And it's to some extent straightforward to understand why, because the 6 moles of carbon are just wasted space. It doesn't contribute anything to the energy or the potential that you can operate in this battery. And so if you replace that, you get a huge gain, order a factor of 10 gain in anode capacity. But on top of that, if you then go to systems that use earth-abundant metals that are sort of intrinsically cheaper, you gain as well. So the holy grail is to create batteries using any of these chemistries that preserve these cost characteristics and then also gets you long cycle life. So that's a challenge that we decided to take on a little while ago. So why is it a challenge? Now it turns out this is sort of like Back to the Future. Because the very first lithium-ion batteries were, in fact, of the design I just said. And they were because people knew what I just said, just intuitively. If you use a metal, it's simpler, it costs less. But what they discovered is that when you cycle these batteries, charge and discharge, these are the lithium ions moving and depositing, you begin to grow these structures on the lithium anode, and these are called dendrites. Their metal structures very easily penetrate the polymer separator, cross over to the cathode, shorts the battery internally. The ohmic heat generated as a result of that electrical short in a volatile electrolyte can actually cause a fire or explosion. And just in case you don't believe me, I decided to bring a real video showing you how this all works in practice. And so the video I'm going to show next is actually of one cell. And the typical Tesla Model S has order 500 to 1,000 of these cells in the car. And what I'm going to do is simulate the short by essentially penetrating the cell with a nail. It's called a nail penetration, a standard test, to short the battery in its fully charged state, and you see what happens. And this thing makes noise, so I don't know at all when it starts. Okay, so I'll click again. Okay, there we go. Looks like something is happening. Okay, so the nail shorts, right? So the heat is being generated, things swell, okay? And this is just one cell, right? Imagine if you have 1,000 of these in a car and an event like this occurred. Unknowingly to you, this obviously is a problem. In this case, it's an abuse, right? So we're abusing this battery. But the point is to just give you a sense for the danger this thing poses, both from a safety perspective, and obviously this battery's life is over after this event, right? So you may get one cycle out of it, so the amortization is not useful. So I'll go back one slide before I go forward to just point out that every metal does this. This is not just special to lithium. Every single metal does this. And in fact, until recently, I used to say magnesium was special. And then 2 years ago, a group from Korea showed that in fact it isn't. That it fails just like the other metals, but we had just not pushed it hard enough in the past. So the question we set out to ask is just why? Why is this so hard? Why do these dendrites form? And what we discovered is that the answer was complicated, and it had two basic parts. So the first part occurs at low current density. And so the sequence of events, and remember, this is not known. This is not a law. This is just sort of a hypothesis based on people's understanding of pieces of this story. So the thought is that the metal, being a metal, will typically react with components in the electrolyte, either chemically or electrochemically, at the potentials at which the metal ions are reduced to plate the metal substrate, to form this kind of layer that is called a solid electrolyte interface, okay? The thought is that the more reactive the metal, the more patchy this interface is, meaning that the more distributed the transport properties of ions are across that interface. And so the end result is that when metal ions are reduced to that interface, they typically reduce into these little bumps. And these bumps are called dendrite nucleates. Now these bumps, for the very same reason when you go into a thunderstorm with a lightning rod, a pointy pole, a metal pole, you will certainly get electrocuted. These bumps attract electric field lines to them. And as they attract electric field lines, they lead to what's called a morphological instability that causes deposition to occur preferentially at the bumps. The deposits grow into these sort of fractal three-dimensional structures, and that is the source of dendrites at low current densities. Again, that's the hypothesis. It first starts with chemistry. The chemistry produces heterogeneity. The heterogeneity produces patchy deposits. The deposits concentrate field lines, and that causes this runaway instability. Now, if you thought, well, why not just go to high current densities? It turns out you get hit by another problem. That other problem is actually an electrochemical instability called electroconvection, where in a battery where you would think there should be no flow, no convection because it's a closed system, everything is stagnant, suddenly flow fields start to be generated at high current densities. And these flow fields have a certain pattern. They have this kind of roll cell pattern where they dump material preferentially at certain spots on the electrode. So the end result is that here by chemistry you get bumps, here by hydrodynamics you get bumps, and the rest is the same. The bumps concentrate the field lines, and the end result is the runaway instability. Now I'm going to spend the rest of the talk telling you some work we've done to address this first pathway. This second pathway is important. We've done lots of work there, but nowadays the batteries we use today rarely are subjected to conditions that are high current density conditions, but they're getting there. The fast charge batteries that people are talking about are getting there. So once we cross batteries that can charge in 30 minutes, we're in this high current zone, and we have to begin to think about this instability pathway. So what can one do? Right, so I told you it started with chemistry, and it ended basically with instability. So the first question was, is this really true? This is a hypothesis. So this is what I'm going to talk about in the talk. I forgot this slide, right? So I'm going to talk about the middle part, the chemistry, and how it leads to morphological instability. So this work is a kind of labor of love, right? It doesn't look like much, but it took a lot of effort. So this is a 4-year odyssey with my colleague in physics, Lina Korkudis, who is probably one of the best cryo-microscopists in the world. And so she built a microscope to basically visualize biological systems in aqueous media. And I wanted to know, could we use that microscope to test this central hypothesis? Is there an SEI on lithium? What does it look like? What is its composition? Is it really true that it has the heterogeneity as claimed? And so we developed this very clever method that is called cryofib with lift out, where the idea is that you take the electrode, the lithium electrode, in a battery, either a cycled battery or a stationary battery, and we very quickly plunge it in liquid nitrogen so it becomes really quite cold, and hence you slow down whatever reactions can occur. We take it into the electron microscope, and we use an ion beam to cut out a section of the electrode. We lift it out and turn it on its side. And that allows us to do scanning electron microscopy now in the plane, and basically what we're studying is the out-of-plane characteristics of the layer that's formed on the lithium. Now, because we do this in an electron microscope where we can do, just observing what it is, at the same time we can do spectroscopy like Auger. We can learn about the chemistry of these layers. And this work was published last year, and it's a fascinating paper that says a lot more than I'm going to say today. But the gist of what we find is illustrated here. That lithium is actually a lot worse than we thought. Whereas people used to think that this SEI layer, this patchy layer, was just about 15 nanometers, 15 nanometers thick. We found it to be hundreds of nanometers thick. It's huge, and it's messy, and it's patchy, and it sequesters things in different locations. And we developed this map to sort of say what it really is. And the map comes from basically doing the yields. So we have regions where fluorides are dominant. We have regions where carbon is dominant, regions where oxygen is dominant, and each of these regions have completely different transport characteristics. So this verifies that the first part of our hypothesis, in fact, an understatement of the complexity of the transport at this interface. And so this was good. Now the next question was, what in the world can a chemical engineer do then? Because if the thing is so bad, and I told you that sequence, you might think there's no getting away from it. So we decided to do what chemies have always done, which is to go up a scale, to ignore the chemistry, and to just say, what if the bumps formed in the first place? Perhaps another way of saying this, if I go out into the thunderstorm with a lightning rod, are there conditions where I can stop myself from being struck by lightning? So that was the question, right? Now, how you answer such a question is writing down the conservation equations, writing down the boundary conditions, and we write these boundary conditions in Fourier space. So we write them in terms of this thing called sigma, which is the growth rate, how the bumps progress in time, and this quantity k, which is a wave number, the inverse of which is actually the length scale of the bumps. So you can learn how they grow, how fast they grow, and how large they become. And the way we do it is basically by solving this coupled set of equations. And I put this here deliberately for the chemical engineers. I understand in your fluid mechanics course, you guys are doing electrokinetics. So all of you know these equations, right? So this is the conservation of mass. This equation basically is a flux balance that says that we have diffusion, we have migration under an electric potential, and the new term we added to this thing is pressure-induced diffusion. So everything in this equation is known but for this new term. And the logic of this new term was that when these bumps grow, remember the plastic separator, they press against the plastic separator. Once they press against the plastic separator, they change its volume ever so little. That change in volume, decrease in volume, causes the concentration of salt to be higher locally. Once that concentration is higher, there's a driving force for salt ions to not deposit on the bump, but away from the bump. And you can do this self-consistently by writing down expressions that relate the stress to the deformation and the pressure to the stress, and then by putting in the pressure gradients, you can solve this whole set of systems self-consistently to understand what this new hypothetical mechanism might do for you. Now it's obviously stabilizing, right? Because it's saying that the faster and bigger these bumps are, the greater the compression, the greater the driving force for things to move away from the bump. So the end result is that the more aggressive the growth is, the more distributed this mechanism makes it. So we were really excited about this because no one had thought about this before. So out of all of this, we can actually then get an expression, and it turns out this expression is analytical for the perturbation growth rate, sigma, okay? And what is cool from a chemical engineering perspective is that there are two dimensionless groups that describes everything. And these two dimensionless groups, P1 and P2, have in them things that you might think might be important in this problem, like the modulus G, like the transference number of the ions, like the current density, like the surface tension. So these dimensionless groups tell us that, physically, this system is behaving like a normal continuum system, and so you might have some hope of stabilizing it using normal continuum variables. So out of this thing, we can actually now plot a map. And the map tells us where sigma, this growth rate, is positive, which means bad, which means the growth is unstable, where it's negative, and where it's zero. And unsurprisingly, the loci on this map are basically determined by these two groups, P1 and P2. The gist of what we discovered is what we're calling the KISS principle, K-I-S-S. I think you know the keep it simple, you know that thing, right? What we discovered is that the answer is keep it small. Keep it small. And where is that seen on this plot? Well, the regions in white are basically regions of stability. And the surprising result for the field is that we can get stability in this model at any modulus of the membrane, right? So the field normally thinks, well, you need a solid state battery to stop these dendrites because you need the modulus of the membrane, the separator or electrolyte, to be large enough so that these bumps can't grow through it. What this is saying, not necessarily. It is saying that under the conditions of this model, you can stop the bumps from growing once you keep things small, once you keep them below this critical dimension PC, lambda CR, that is set, in fact, by this dimensionless group P2. So that's kind of a nice testable result. And my group has actually been testing this result in all sorts of configurations. That's all we do now, just test it. And you can imagine that you can test this in a variety of ways. So my first set of students tested it in what we call model systems. These are membranes where we can, in fact, control very precisely the length scale in which the deposits occur. So these use a material called AAO, anodized alumina, that you can make to form very beautiful nanopores that are straight and that are macroscopic. So with a single material, you can really test this model. Is it really true that on a length scale below this critical value, you can stop bumps from forming? We also have a second material that is going to be like a subplot to my story. These are the so-called nanoscale organic hybrid materials because the dark spots, the yellow spots, stop ions, and the open spots allow ions to move. We like them because chemistry you put on the surface of the particle could be used to now not just control the length scale of the bumps, but to regulate how ions move towards those length scales. So we have additional sort of backdoors that we might use. So So I'm going to tell you really quickly that this thing works really well. And I'm going to go a little bit fast because I want to tell you where it doesn't work. That's almost as interesting at times. So the approach we're going to use to evaluate success is one that actually my colleague from not so far from here, Natasha Balsera, and his group popularized. And in this method, you basically create a cell. The cell has two electrodes. In this case, they're metal foils because we're testing the stability of metal deposition. And there's an electrolyte, and the electrolyte could be whatever you want, okay, between these two electrodes. And so what you do is galvanostatically, which means at fixed current, you strip metal from one electrode for a period of time and just dump it on the other one. After you're done, you do the reverse. And the thinking is that if I measure the voltage, because this thing is done at constant current, if the resistance remains the same, then the peak-to-peak amplitude of the voltage response should actually be the same. So it should sort of follow the current. What they discovered is that very quickly, in this example, after roughly about the 50th or 52nd cycle, there's a sudden drop in the voltage. And when they opened the cell, unsurprisingly, the dendrites had crossed and shorted the cell, which means the resistance has dropped. So this measurement gives you a very simple way of just determining in a closed cell when it has failed by dendrite-induced shorts. And so we did this measurement, and this is a lot of data I know, but I want to go a little bit quickly here. So we did this measurements. This is for the anodized alumina. The red is what happens when you don't have the nanoporous alumina. So these are 20 nanometer pores. So basically at first, with just the normal electrolyte, we observe nice peak-to-peak values that are stable, and then they drop to 0. Then they pick up back again, and then they drop to 0 and stay at 0 or close to 0. So roughly after about 150 hours, this cell is no good. It's completely shorted as expected. The surprise was that with the 20 nanometer anodized alumina, remember these are porous materials that have a liquid in the pores. The same liquid that's used in the red one. They just go on and on and on, okay? And then the trouble became, how does the student graduate, right? So if I just keep going, then when does this experiment stop? So I decided to do what professors do, which is to make this thing work harder. So we start pushing it at higher currents, and it just goes on and on, okay? Indicating that the 20 nanometers membranes, we were able to stop the dendrites from proliferating. So this is some kind of qualitative support for the model, but the model didn't tell us 20 nanometers, it told us 250. So we still have some ways to go. So one of the beautiful things about anodized alumina is that we can actually now change the pore size, and so this is what I'm showing you here. So for the highest current, here's what occurs as you change the pore size. So 20 things look good, 50 they're still good, 100 they get shaky, 200 they get a little bit shakier, but still more or less stable, but by 300 everything falls apart. And so I actually didn't believe this result because it's just too cute. The model says 250 and this failed somewhere between 200 and 300. So I decided to have the student go look inside the pores because I wanted to know, is there some mechanism where the dendrites might actually in fact grow inside the membrane? And so we basically looked first on a large length scale, and you can kind of see the sharp interface. This is a lithium metal. This is the anodized alumina. You can see the sharpness of the interface after it's cycled, indicating at least from the macroscopic scale, it appears that the membrane just stops the penetration or stops the growth at the interface with the lithium metal. But I, of course, was not happy with that. So I had Zheng Yuan use the same cryo-FIB technique to cut a trench inside the membrane to kind of turn it on its side to see if there's any lithium inside. And the answer is no. So we can basically say that by controlling the length scale below a certain value, where we think surface forces like surface tension and interfacial elasticity dominate, we can essentially use natural forces to stabilize, to make more smooth the deposition in this example. Now, my students, of course, went wild. And so no one is going to sell you a battery that uses AAO. So the thought was, could we do it with a polymer? And so what I'm plotting on the left axis is actually the reciprocal of the lifetime of the cell. So ideally, you want this thing to be infinite, so its reciprocal is 0. So 0 is good in this context. And I'm plotting it against the modulus of the material, and I'm plotting it for different systems. So polymers, and you can see we're close to 0 for moduli that are a little bit below what's normal for an entangled polymer moduli. For hairy nanoparticles, it's good. For the anodized alumina, you've already seen that. And for the crossing nanoparticles, it's here. In fact, the only exception are older results done by the group that invented this method using block copolymers, where the intersection occurs almost exactly at the modulus of the metallic lithium, indicating that our approach does not work for this particular system. And that was a bit of a puzzle, and I think I know why, but I don't usually say it in public, all right? But for whatever reason, this one example, which is I think the most elegant example, which is a block copolymer that just spontaneously forms nanostructured domains, this method does not appear to work. And we can come back to that, all right? So that's good. So everything looks rosy, right? And the advisor should say, student, graduate, you did a great job. Well, I wasn't happy. I wanted to do everything, right? I wanted to do everything. So we did lithium, we did aluminum, we did zinc. And with lithium, we're up to 2,000 cycles with no evidence of dendrites. For aluminum, we're up to 30,000 cycles, charge-discharge cycles, with no evidence of dendrites. For zinc, we're up to 10,000 cycles with no evidence of dendritic shorts, indicating that this is not a technique that's just limited to lithium because it's physical. It seems to be applicable to any metal. It's as potent to some extent as the problem in solving the problem, and we think this is because it relies on physical forces to solve that problem. So we built a fish, right? This is actually kind of cool. I didn't have this idea, but I enjoyed working with this very creative mechanical engineer who was thinking about the robots of the future. How are we going to power robots of the future? So we basically built a lionfish, and this work was published just last year, where we used the zinc concept in a flow battery. So basically the bloodstream of the fish was the cathode. So this is a really kind of cool idea that may begins to mimic us. And if you go on the website, this video actually plays, and you will see the fish isn't doing fancy things, but it is able to move, okay? And so we're in the midst of doing the next generation fish that hopefully will move a lot faster than the ones you're going to see in that video. So that is kind of fun. So one of the fun things about research is that unexpected things happen. And especially when you do the research with a diverse team of researchers who come to these problems with their own perspective, their own background. And so one of the persons who joined my group at this time was actually a postdoc who had an ionic liquid background. And so what he saw was not the things I said to you that were great. He just saw these hairy particles, and he saw that the fact that each particle had like 1,000 ligands on it, and you can use that to regulate things in a battery. And he said, aha, I may be able to tether inside a battery agents that could be used to solve the other problem, which is the fire problem, the safety problem. And the idea is that because these agents are tethered to things, they can remain kind of benign when the battery is working fine, but when they receive some kind of stimulus, like a heat wave, they break apart and things go wild. And so this started the company called Gnomes Technologies, and this company came out of my group. That postdoc is the CEO of that company. And this video shows you what happens. It tells you the power of his idea. So that's the same experiment, the same cells that I showed you at the beginning. And this is a slow video, but you can see smoke, so it means something bad has happened. But if you wait and wait and wait and wait and wait, you will notice that this cell swells, but it never catches fire. And so just last week, he got the patent rights for these things, and they're just sweeping patent rights. And so we are pretty excited about the ability to not just solve lithium. This is a lithium-ion battery. So the thought is that the safety point that Jennifer made, if we, with some luck and lots of funding, we'll be able to perhaps make lithium-ion batteries that you don't have to have a safety minute that discriminates against lithium-ion batteries. Okay, so this is a great result. Now, and so that's a little bit about the company. I put it up here just to say my wife, who is actually the person I had to beg for the money, because it's my money that started this company, is actually an alumnus of this department. And so while she was a grad student, I was a grad student on the other side of the hill. And so she sends her best wishes. Okay, good. So, so this is all going great up to now, but I wanted to know more. So we have these two-dimensionless groups, and I have not told you anything about them other than their effect on this critical pore size. So what we decided to do is to play with one of them, this group P2, because P2 is the reciprocal of the surface tension, something that we thought we can change very easily by adjusting the chemistry of the electrolyte. In fact, if we use a goniometer to measure the surface tension of the lithium electrode, by dropping droplets that contain different mole fractions of a salt, lithium fluoride, that is poorly soluble in that electrolyte, we find indeed that we can actually increase the surface energy. I said increase. We can very rapidly increase the surface energy on the lithium electrode. So this tells us that we're actually controlling P2. And so the question at first was, okay, so if then we measure the lifetime of cells, would we see some sort of correlation with this result? And we got a really big surprise, right? So the really big surprise is this point here. Okay, so this is a liquid electrolyte, no nanopores. This is just a simple electrolyte, added the lithium fluoride, and it's stable like you wouldn't expect. And that was unexpected. It obviously is a completely disagreement with the model. And even more recently, we show that this concept is quite general, that certain types of materials, once you deposit them on the metal electrode, they're able to keep the bumps small just on their own. They don't need this membrane to do that. So this was kind of cool, because it means you don't need our membranes after all to be successful. You just need a right interfacial agent, which to some extent you might have predicted from the fact that this started with chemistry. Right? So everything I did in the analysis essentially just ignored chemistry. These salts appear to be influencing the interfacial chemistry. So just briefly, we decided to understand how this might be influencing the interfacial chemistry. And so this student, who's actually now looking for academic jobs, who's exceptional, by the way. You guys, okay, he's like exceptional, all right? If I had to hire me, it would be him. So SNE basically worked with a group that developed a method called joint density functional theory. So many of you have heard of density functional theory. Its Achilles heels is that it cannot handle solvents. And in the joint density functional theory, which was developed by Thomas Arias at Cornell, the idea is that you can actually capture the configurational state of the solvent as well. So it's suitable for batteries. And the discovery that SNE and his colleagues made is that this lithium fluoride salt, if you compare the activation barrier for add-atom diffusion on the lithium fluoride salt in a vacuum and in the electrolyte, you find that it's substantially lower than lithium carbonate, which is the electrolyte component that typically will be present in larger fraction at the interface. If you use things like lithium bromide, the results are even more dramatic. And I see Kristen in the audience, and you worked on this when you were in the group, right? So lithium bromide, Kristen was one of our undergrads at Cornell University and did some very nice research that was published. I think she's a co-author, in fact, of this paper. So, the prediction was that the add-atom diffusivity was sped up because the barriers to transport were lowered by the presence of these salts. So we did a lot of fancy things. So the question was, how do we verify this? How do we measure this? And it turns out there's a very old theory by Barton and Bockris that tells one how by measuring the overpotential during the early stages of deposition, you can get out the physical variables like the real surface energy. You can also get out things like the transport properties in the bulk. And we amended this model to include the surface diffusion. And so we can, by fitting this model to data, we can get information about lots of things that are occurring at the interface. And so if you minimize this overpotential, in other words, if you look at where it's the distance from zero is the smallest, you can actually get this very nice expression that tells you how the current influences the size of the bumps of the nucleates, and the fitting parameters are encapsulating these things that you don't know. So we did that, and this is what the results look like. So we didn't use the lithium fluoride per se, but use a salt that decomposes to form lithium fluoride on the electrode, because we wanted it to be completely uniform to not interfere with the model. We measure the bumps or the nucleate size at that minimum point for different current densities. We fitted them using ImageJ, and out of that we can get things like the average size of the bump and the standard deviation. We can then fit the results to the model, and this is what you get. So this is our results. Large error bars because we're now averaging over many bumps, but the fit is actually reasonably good. We were so impressed we decided to fit it to all the literature data we can find, which is not a lot, but you can see the fit is pretty good. And out of that we can actually get an estimate of this so-called SEI diffusivity, the DS value. And what we find is, perhaps unsurprisingly, the value rises by a factor of 2. As predicted from this DFT analysis. So the DFT says it should rise by a factor of 5. And what we see is about a 2-fold increase, suggesting that this is the process by which the lithium fluoride works. So that's everything I wanted to tell you today. So the very first part told you that we've stumbled upon this approach using just simple continuum theory that allows us to design electrodes, electrolytes, and separators along this so-called KISS principle. If you keep the length scale of the nucleate small, small scale forces are enough to prevent dendrites from growing. And so this is a very powerful discovery. The discovery stemmed from this idea that the most unstable mode of growth, measured in terms of that perturbation growth rate, can be influenced by membrane structure. And the last result is just as interesting, because it says you don't need any of that material science stuff. You just need to understand salts. Just a little bit of salt that lowers the barrier for surface diffusion can go a long way. And so these are the students who did the work. I do a lot of work with this guy. This guy is a great theorist, and this guy is a great polymer scientist, and these are the people who funded it. And so thanks for your attention.
Okay, well, we have time for questions, and we're going to use the microphone so that everyone can hear. So, yes. Who has a question?
We discussed earlier the car companies that you interact with, and I was curious of the two mechanisms to prevent dendrites, so the new one, the salt, the chemistry versus the physical stuff. What are they most excited about?
That's an interesting question, and the answer is all of the above, right? So the interesting discovery, and this is actually one of the virtues, or I'd say values, in starting a company as a professor, is that you get to learn that the things you thought to be true are mostly wrong. That the car companies have no control of the batteries that go into their cars, and many of them have no interest in having any control. So they can tell you they like everything, and they can pat you in the back, but they can't spend a penny on that because someone somewhere else is usually making that battery for them. And so what we discovered is that you now need to find that someone somewhere else, and that someone somewhere else typically has no interest in changing anything. It doesn't matter how well it works. They want to keep it just the way it is. And there's some justification for that, in that the cost of retooling and so forth is just so high that unless this thing, is going to be sold to everyone, they're not going to gain much out of it. So what we've heard from that community is the stuff that the postdoc did, where you add just a little bit of something in what they already have, a so-called drop-in solution, is about the only thing that there's interest in existing companies. But obviously, that then creates an opportunity to the extent that in itself is not disruptive enough. Then it gives a chance for a new company to essentially build batteries and go through the entire qualification process to ensure. But it's a great question. It's important, I think, for students to get that experience, you know, interacting with companies, because often the things you hear in the news are far from the truth. The supply chains are very complicated, and it's rare that you can ever find the right person to talk to that can make a change like this.
Your question.
So you've made lots of, the batteries were on a very small scale. Is the barrier between the small scale and like a full-scale battery a supply chain one, or is there another physical barrier to summing all those?
Great question, yeah. So that's very perceptive. You must work in batteries, is that right? Oh, well, even better question, yeah. So all the stuff I told you were with coin cell batteries. These are little button cell batteries. And there are two reasons why we work with coin cells. One is that it doesn't take a lot of material, so we can make our milligrams and be happy. But the second reason is the safety moment, right? Just imagine if one of those big cells shorted when a student was assembling that battery. So this is actually one of the real drivers for starting the company, that there are certain things we just could not do in university facilities. And so, so you are right that there's a step up that requires us to now explore these improvements at scale. And the gist of what we've discovered is that things tend to be a little easier when the cells get bigger. And this is in part because you know, there's more electrolyte. The casing for the cells is perhaps not as hard. And so we were able to be more effective, and the quality of the metals and so forth are better that are used in the larger cells. So this looks very good. I mean, the challenge for us now is which chemistry is the winner, right? So aluminum is earth abundant, right? It's the third most abundant element on Earth. And so you think that's a natural choice. The problem is that its potential is low. So the overall potential of the batteries that you form are low. The aluminum is trivalent, and so the problem is that you've got to find a cathode that can work with it. Zinc is likewise exciting, but it's divalent. Its potentials are low. It has very complex chemistry in aqueous media. So there are lots to figure out, but the point is that it's not at this stage a challenge of scale. Yeah.
Could you share your perspective on how you would prevent dendrite growth when you have high current densities, the heterorotational thing?
Yeah, yeah.
That looks like where the future is headed, right?
Yeah, yeah.
How can that Tesla chargings?
Yeah, so we don't have good answers. Giandi has some answers to that question. So we have some nice work with Giandi 1, where in microfluidics he has shown that imposition of flow could be effective in providing more uniform deposition at high current densities. We've done some work that shows that polymers, that if you add polymers to a liquid electrolyte, there's a phenomenon known as elastic turbulence. This is, and so you're a fluids guy, so I can say this directly, that flow is actually a stagnation flow. So there's a lot of stretching near the tips. And so what tends to happen is that when you stretch the polymers, they orient and provide a very large hoop stress, and then they relax. And ironically, that doesn't stop the dendrites from forming. It actually creates unsteadiness in the fluid flow. And that unsteadiness actually makes the flux of ions towards the interface more uniform. So we have these results, and they're kind of exciting. And one of the exciting elements of them is that we can achieve this at extremely low concentrations of the polymer, provided its molecular weight is big. So the idea is to have a very high Weissenberg number in the flow.
Other questions?
I heard you guys like to ask lots of questions.
I'm just curious, is it ever possible to reverse the growth of dendrite?
Well, there are people who claim it is. So one of the things that we've discovered that I actually didn't go into a lot in this talk, right? So you might have noticed that when I showed you the first red oscillations, They started off where the peak-to-peak amplitude is about the same, and then they plummeted to 0, but then they sort of somehow became alive again, right? And what we discovered is that there's a process called orphaning that occurs. So once these dendrites form, they're actually quite brittle and spindly, and they can actually break away from the electrode. And so they don't kill the battery because they can't grow between the electrodes, so they're kind of safe in that sense. The problem is that when they break away from the electrode, they're no longer electrochemically active. So you essentially lose that amount of metal from the electrode. So you can reverse them in a sense by using mechanics to break them. The other way people have shown is to use heat. So people have shown that if you in fact use a heat pulse inside the battery, you can melt them near the roots. And that achieves the same thing. It breaks them away, and so they can't harm the battery. But what they do, obviously, since the amount of metal in the anode is now reduced, because you've lost some of it, then the overall capacity of the battery fades.
Thank you. Before we thank our speaker, just two quick announcements. We have a wonderful reception on the patio with great food and drink, so please, I hope you can stay for that. And we also wanted to give a gift to kind of for memory of this occasion, and let's please thank our speaker.
Thank you. I guess he is.